And this fast summation method, okay, I'm getting a recording message here. The fast summation method that's most well known is the fast multipole methods. Those were pioneered by Leslie Greengard and Vladimir Rocklin. And you also have FFT-based methods. And all these methods, they're approximate in the sense that you're not going to get the exact solution or the exact sum, but you are reducing the computational work to be proportional to n or n log n. But you have a constant in front, the C epsilon, and this constant depends on the accuracy that you want. So for higher accuracy, it will get more expensive. So our contribution to all this is a set of the spectral Ewald methods, and that's a set of spectrally accurate FFT-based methods. And these are based on so-called Ewald summation. That was one of the unknown, maybe, words in the title. So I'll tell you what that is. And I'm going to mainly discuss this for electrostatics today. And I will briefly just mention the extension to Stokes equations at the end. Oh, oops, sorry. So what we're doing now, so we want to compute the electrostatic potential. This is very common, for example, in molecular dynamic simulations. You need to find the electrostatic potential or force or energy, but here I'm just writing the potential. And it's very common then to have periodic boundary conditions. So because you don't want things to be in a vacuum, you want to take these replicating boundary conditions. But here we want to think about it more generally, like you might like it to be periodic in all directions, or you might want to have periodicity only in two or in one direction. And definitely when you think about solving integral equations, like for the Stokes equation, certainly you could want periodicity in only one direction. So we will try to think about this more generally. And to make these sums make sense, for especially the triply periodic one, you assume that you have charge neutrality, that the particles that it actually sum to zero. So what Ewald did when he works on this, so this is the name Ewald summation, was to think about how do you actually how can you actually compute this conditionally convergent sum? So this sum, you can see this as if you get this from a convolution of this Green's function and a point source, a point charge, if you'd like, in electrostatics. So what you do is that you can write each point charge as your delta function, and then you subtract off a screening function, you call it the Ewald screening function, and you add the same thing on. And the idea is then that this gamma E should be chosen such that the first part, when you look at the result you get, will be short-ranged, so it will be local, and you can treat it in real space. And the second part, that the solution from that will give you something smooth that can be treated in Fourier space. And so the sum looks like this for electrostatics. This is the classical sum then. So suddenly we have this parameter psi that popped up. So this is a decomposition parameter. So if you increase psi, then this C, which has an exponential decay, is going to decrease even faster. But whereas this exponential decay in K-space that you see is going to be slower. So you can control this. And the idea with an accelerated method is to make the FFT part faster to compute. So you want to accelerate that. And if that one is faster to compute, well, you can adjust your psi to reduce the work in the real space part. And if you do that, you will get the proper scaling here would be an order n log n method. And so, but as we said before, so it will be faster, but it will have an approximate evaluation. So you will have to control your errors here. So we will think about first the triply periodic and then go to the others, which are not as classical. So, but then you have a class of methods called the particle mesh Ewald methods, and they all follow the kind of same steps. So you have these irregular points in space, but you will introduce a regular grid, and you have to place somehow these points onto the grid, which you do with some kind of you interpolating or window or smearing function, many names. I will call it window function. Then you compute the FFT of this grid function, and then you will apply a scaling. You will multiply by some function in K-space, a modified Green's function. You will take an inverse FFT to go back to real space. So now you're back on a grid. And when you're back on a grid, you're going to interpolate from the grid to the target points. And you're going to use the same window function as you did before, because you want to know the solution in points which are not on the grid. So you have to do that. And so there are many different methods in the PME family, and the way they differ is by these choices of the spreading or window function, if we call it that, and the modified Green's function will be tied to that choice. So when we do this, we will have two sets of errors. One is that we had infinite sums before. Now we're only thinking about k-space right now. We will truncate that at some point. How many modes we pick out, we include depends on our grid size. And then we will get the truncation error. But then in addition, we will also get some approximation errors. So in electrostatics, we have some very well-cited, highly cited references for these kind of methods. So our methods around this, the spectrally accurate FFT-based methods, we did originally for triply periodic domains, electrostatics, Stokes, starting a number of years ago, and then we've extended them in different directions. And today I'm presenting a unified framework from triply periodic down to free space for electrostatics. And we started this work some years ago, but then for practical reasons or different circumstances, it was kind of halted, and now we have just finished it, and we are also working now on extending to Stokes equations. So I mentioned the window function several times. How do you spread to the grid? So in GROMACS, for example, which is a big package for MD simulations, then you use B-splines of a fixed order. But if you do that, that means that your approximation errors will go to like order h to the p, where h is the grid size of the regular grid. So you need to increase your grid size to reduce your approximation errors. So our approach has been different, where we have used Gaussians that we can scale independently. We have p points in the support. We say we have p points in the support, but we can scale it so that to use it optimally, which means that this is an old picture, but if you look at the number of grid points you need to get to a certain accuracy, you can use much smaller FFT grids if you take this approach. And today we're also going to look at another window function called the Kaiser-Bessel window function. So here are the two window functions, a simple Gaussian. First, the window function is composed, it's a product of three one-dimensional window functions. So this is the truncated Gaussian. It's just truncated outside of some width. So we have p points in the support. We have the Kaiser-Bessel function, which has as in the name, it has a Bessel function here. And we know the Fourier transforms of these, so we can use them. So this is what we will use to spread to the grid. So now I'm basically doing the same thing again, just showing you some formulas. So I'm saying, okay, we start with the k-space formula. We have this one. What we're going to do is we're going to evaluate, we're going to apply, we spread to the grid using W, which is our window function. And then we take the FFT, and then essentially we've gotten the quantity to the left, the h hat k. So that includes quantities that's up here, but it has an extra W hat k. So our scaling in the middle, the modified Green's function, is going to have the first factor that you recognize from above, but it's going to have this factor of the window function, the inverse of it to the power of 2, which is because we need a deconvolution to undo the effect that we use the window function here, and we will also use the window function in the last step. So that's why I said, so what you multiply here will depend on your window function, so to get the accuracy you want. Okay, and then we take an inverse FFT, and then we gather from the grid again. So these were the steps we already went through. Now, this is triply periodic. So I said that we wanted to look at different periodicities. So what happens if it's not periodic anymore? So the idea here is to still think about it in the Ewald kind of sense. So if we look at for all periodicities, so I'm going to have a super index here, D. So 3 would be the triply periodic. We have the same structure. So we have a real space part will be the same in all cases, except that the summation, of course, will be different, how many periodic directions we sum over. But it's still local, so it decays fast. The self-correction term, which I didn't mention before, but it's there because You're not supposed to include the action of yourself or the contribution of yourself into the sum, but part of it will be included through the Fourier space. So you have to remove this part. But the case-based term will differ. This is where the difference will be seen, especially when it comes to the periodicities. So really the expression will be the same, but we don't have discrete. When we have a discrete sum, a discrete Fourier space, we don't have, they become integrals. We're working with Fourier transforms, continuous ones. So they become integrals in the non-periodic directions. So looking at it, we can see it this way. So here we have a triply periodic sum, the one we had before. They're all sums. Then we remove one periodic direction, say this one is not supposed to be periodic. We don't make any extensions there. Then that will turn into an integral over that variable. Here we'll have two integrals. In the free space, it will be just this Fourier convolution, in the Fourier integral completely in all three directions. So this is what happens as we go down, and we replace sums by integrals. So yes, so when for example, if we look at this one, when k1 is equal to 0, so the periodic wave number is 0, then we will have a point when k2 and k3 are 0, where this will be singular. And so that is not so nice to discretize by numerical methods, because we would, so this is something that we'd have to think about. So what we do is we split this. So we write the Fourier part with the one for all the modes when k is not equal to 0, the discrete mode, and 1 when it is 0. And these integrals can actually be evaluated, and you can find closed form expressions for them. So you know what they are, but they include they contain special functions like error function, incomplete modified Bessel function, etc. So not very simple functions, but you can evaluate them. And actually, based on regularizing and periodizing such special functions, there is Nestler and al. Introduced an FFT-based method to actually do, to have a way of computing these sums. So we have done something different here. So what we are going to do is instead we're going to think about these integrals, and we're going to discretize on these regular grids to enable the use of FFTs. But we will have to think about first these singular integrals, how do we handle them? And then also, do we get enough accuracy for the other modes if we just discretize? So this is two things that we have to deal with, think about. So this is something interesting here coming up that I will show you, and it has implications not only, it's a good technique to know about, not only in this context, but in other contexts too. So the Fourier part for the free space case is the solution to, we have a superposition of these Ewald screening functions with some strengths here. So we're solving a Poisson equation. In the singly periodic case, we're solving one in 2D. In the doubly periodic, it remains one in 1D. But we have to solve these kind of free space problems, right? And so we can think if we want to, so now let's write it like this, where G is just some smooth and compactly supported function, and we want to solve this equation. Well, we can write this as a convolution between the Green's function, which is just 1 over the distance, times this right-hand side. Or we can write that in Fourier space. But if we think about, so if we now think, as I said, we assume that G is compactly supported within some domain, and we seek the solution within the same domain, then we know that between the 2 points in this, if we think it's a cube, there is a maximum distance. It's a square root of 3 times L, or L tilde, I call the distance. So then if we take our Green's function and we replace it with a function with a superindex R here, cap R, and we let it be equal to the Green's function as long as R is smaller than that distance, which we set to the maximum distance between 2 points in the cube, and 0 otherwise, then we haven't changed the solution, as long as we stay within the cube. Otherwise, we have changed it, but as we haven't changed the solution. So they will be equal. There's an equal sign here. Okay, so why is this useful? Well, because if we took the Fourier transform of the Green's function, we get 4 pi over k squared. It's like 2 derivatives in, and you go to Fourier space, it's 1 over k squared. But if you look at this one, it actually, you get something different. And what you have is that you have a finite limit at k is equal to 0. So instead of a singular function, you have something with a finite limit. And since we wanted to discretize this with FFTs, this integral, and actually evaluate it, of course, it's much, then we can numerically handle this. So we can use it. We use a spectral trapezoidal rule because it's a compact support. It's going to be spectrally accurate. And we can do this, and we just discretize and use an FFT to evaluate. And we can do this also in the lower dimensions, and we have the same kind of approach to do it. So I will introduce this. This was the original Green's function that we had. In the sum we had, you only saw a 1 over k squared. And now I'm going to call it something. So I'm going to do g hat 3p. And then I have a 2p, 1p, and they will differ. And this comes from this k is equal to 0 mode where we've solved, where we have this trick to actually rewrite it to get the finite kernel to be able to discretize for the free space problem. Okay, so this is just a way putting different indices to actually have it in the same framework. But this is what's going on. Okay, so this is how we can treat the 0 mode. So what happens if we try, let's say we have this one. So now we have a sum, 2 periodic indices here, and we have an integral in the third direction. So we have an integral only in one direction. And this, we introduce this first part here will be capital K squared. Well, capital K squared, we've taken care of the case when it's 0, so it's different than 0, but it might be small. So what is the accuracy if we apply a trapezoidal rule to this? Well, by using a technique that was actually introduced in the 70s, which has, by contour integrals, residue calculus, we can show that if we look at this integral here, then this is actually the error that the trapezoidal rule will do. So delta kappa here is the step size in the K space because the integral is in K space. So this is the one that we have. So if we translate this to what we're doing, then if we have in the free space direction, if we extend the domain a little bit, I'll show you in the sketch Y, and we upsample with some factor SF, then our step size in the Fourier space will be 2 pi over L tilde, that's the usual one. And then the way you reduce is this by upsampling. So that's the upsampling factor. And if you do that, this is the error that you'll have, or we made an approximation, a small approximation here, but that's the error that you will have. And what you can see is that if K bar is large here, so for large K1, K2s, this will decay very quickly. But if K bar is small, this will be, then it will go slower, and you will need an upsampling factor to actually get a good accuracy in your error. So you don't want SF equal to 1. You need it if K bar is equal to 1. Then you just get e to the minus 2 pi here, essentially. Okay, so we want to have that. So we can use a different upsampling. So what we're saying here is essentially that, okay, we have several different cases. We have the discrete 0 modes where we have one way to treat them. We have the small discrete wave numbers when we need upsampling, and we have the large discrete wave numbers when we need no upsampling. So to be able to be flexible here, we have implemented what we call an adaptive FFT that can take different sizes, different upsampling rates for different modes. So we will use that in our computations. So thinking about parameters, there's a range of parameters now. For the triplet periodic, we didn't have so many. In the K-space part, as soon as Xi has been decided, which balance with the real space part, we have the grid size to pick and the number of points in the support of the window function, essentially. But for the others, we have a number of other parameters which has to do with these different upsamplings when it's not fully periodic. Then we have to choose more. So I'll get back to this in a second. But just now, I'm kind of repeating the algorithm again, but with a little bit of a sketch. So I mentioned an L tilde. So this is our L tilde, a little bit of an extended domain. We interpolate the onto the grid, and we're going to do now this time instead of this adaptive FFT to go to Fourier space, and we're going to scale And this time we're scaling with our modified Green's function. So it's not just a simple 1 over k squared, it has some other formula, but you just apply it. So it's different then for how many periodic directions you want. And then we do the same in an inverse, adaptive inverse FFT to get back to the grid, and then go from the grid to the target points, again using the window function.
Anna, we have 2 minutes more.
2 minutes more. Okay, I thought I had 4, but okay. So then we can see here if we have these two window functions. If we now take the grid to be large enough, so the approximation errors dominate, we can see these two window functions that this Kaiser-Bessel window functions is actually decaying faster. We can make it have smaller approximation errors. To make this efficient, we have made, instead of evaluating Kaiser-Bessel functions, you don't want to do that. We have a binwise polynomial approximation of it that doesn't, as you see, doesn't hinder the accuracy. So to think about parameters in the method, there are some, as I said, and when the grid size is tight, then these approximation and truncation errors will a little bit, intermingle. So we have a kind of an algorithm for how you select all these parameters. So it's done, of course, we describe it in the paper, and it's done automatically to give you a certain RMS accuracy, RMS error. So here, if we look at the cost, then these are just for the window function spreading and such. Then the Kaiser-Bessel is of course cheaper. The FFT parts, they're very similar in the grids. And when you add them together, so this is the lowest line is always triple periodic, it's most cheap, and then you go up and it gets more expensive. And the blue group is the Kaiser-Bessel, which due to this will always be at least a bit cheaper. So those are the ones that we will actually use. So as you said, 2 minutes, I can't really spend any time on this, but we made also in the paper a comparison to the FMM. It has all the details, just showing, of course, our code is not optimized. We had an easy to install version of theirs, but it's a new library, and it's kind of showing that we're in the same ballpark here. This is the FMM kind of in the middle. These are larger number of points. Two different systems, where the FMM is more favorable because it's adaptive in difference to an FMM, to an FFT-based method. So can I take 1 minute to say something about Stokes?
Yes, sure.
Okay. So it is the Ewald summation formula for the Stokeslet is similar in structure to the electrostatics. So with the need and the use of adaptive 3D, FFTs is similar. But we have to think more then about the solution of these free space problems, what we can do and how we can do it. So the trick that I showed you, this truncating of the Green's function and then getting something finite in the Fourier space, that was for a radial functions. So what we do actually to handle it for the Stokeslet, which is not radial, is that we write the Stokeslet, we write it using the relation to the biharmonic Green's function. And then we do this treatment for the biharmonic Green's function, and we can come up with a truncated Stokeslet like this, which also will have then a finite limit in k-space. And we can do things similarly, and then we get a little bit different problems to solve. But we can do this quite similarly to what we do with this. But we have left to look at this for the other fundamental solutions, like the stresslet, if that word says anything to someone, if you worked on that. Okay, so as you told me, I am a bit out of, maybe I will just leave this up here then and finish here. So thank you.